Hello everybody. So I just wanted to so let's continue with this summary series. We are now starting the lecture series 3 that talks about analysis of algorithms. In this series of lectures, Professor Robert talks about how the mathematical basis behind analysis of algorithms. Okay, so let's talk about that. So initially he talks about there are 4 different people who are kind of involved when you think about a problem. First is the client who just wants to get his or her problem solved. The programmer who actually is going to be implementing the problem. The theoretician who wants to understand, okay, what's the mathematical basis behind this? Can this be solved? How quickly can this be solved? And is most of the time coming up with the actual algorithms. And the student, as a student, and the final one is something that who learns and studies, and we all kind of play each of these roles from time to time. Sometimes we can be clients, sometimes we can be programmers, sometimes we might to come up with a new algorithm ourselves. So this is about some history behind it, that excuse me, that this is not new. People have been talking about this for a while. Charles Babbage talked about it a long time ago. And why would you want to do something like that? So that you know how so you know what to expect. You typically don't want to just be surprised that, oh, I didn't knew that this is going to take so much time, or this code is going to be so much slow, or it is going to take so much memory. So the idea is that you figure things out beforehand, once again plan and kind of reason about it, and then implement it. Why would you implement something that you would not succeed or meet your expectations? And once again, here he talks about an example of a problem, discrete Fourier transform, and how it has enabled to get a lot of neat things right now, and how a lot of modern technology is built on the top of it. And he was able to figure out an n log n instead of an n square brute force algorithm. And this is where you look at the growth of the algorithm as to how linear goes, linear, and how quadratic goes. As you can see that quadratic is just way too faster and quickly goes out of scale. And there is another n-body simulation, the challenge. Okay, so how do you do this? You observe, you hypothesize. What it means is you kind of figure out, okay, I think that it should be this way. Then you predict, and then you verify. You actually run and validate that does this make sense, and then you also make predictions and can figure out, okay, now based on this, I think my model is correct. And the principles are the experiments must be reproducible and they must be falsifiable. Hypothesis must be falsifiable. It means that you should be able to prove it wrong. Okay. So now let's look at this, the three-sum problem. So the idea of the three-sum problem is, given a set of n integers, how many triples sum exactly to 0? Okay, so given any so what's the number of triplets that you have? The most basic one you can imagine is an order n cube, where you just have 3 for loops, and they are you're adding all these 3 sums. So that's that's the most obvious one. Now you figure out, okay, let's try to run this. How can you do it? You can do through some stopwatch code or something like that, and figure out how much time does it take given any number order n. You measure these things and you look at these times. Given n is 250, what is the time in seconds? And you say, okay, yeah, this is what you can see for the performance of your algorithm. And now you want to predict that, okay, given n is 16,000, what would be the can you make a prediction? And in this case, there are multiple ways to do this. The first is you can just do a plot. A standard plot is problem size by running time. You just plot n by tn. A better thing to sometimes do is just do a log plot, and in this case you can see the slope of the line is the growth of the curve. In this case it's n cubed, so the y is equal to mx plus c, m will be equal to c. And how this works, just look at this. You take log on all, both sides, and b is the slope, so y is equal to mx plus c. So that's the idea. M is b, which is n raised to b, and in m is, in this case, the growth of the curve. So that's what, in this case, if you just do that analysis, you'll get b to be close to 3 and seeing some constant, and you get it as kind of a what you basically get is it is an order n cube algorithm, which kind of makes sense, and hence you will be able to predict something, 408, and when you run it, you see it's very close to the prediction, which is 410. Doubling hypothesis. Okay, so that's that. Run, and what's the quick way? You double the size of input and you kind of figure things out anyway. So that's the idea. So this again talks about that. Okay, so now comes here. So the interesting thing here is the things that are constant are the algorithm and the input data, but things change. Your CPU, your machine changes, where you're running on it changes. So all these things change. So it's hard to figure out that, okay, my algorithm that runs this, that runs with X seconds, how much time is actually going to take it on that different machine. That's pretty much, it's hard to figure out because the performance characteristics of the underlying system may be different. But then if you do this mathematical analysis that it is order n cube, then you do get a good sense as to what is the growth of as the input size increases, and you get a very good sense of how your algorithm is going to scale with respect to input. And so Donald Knuth actually came up with this idea about mathematical analysis, and the idea is that is actually very simple, that what you do is you figure out each of the operations, how much time is it going to take, and then just add them up. Okay, that's add them up, and that's the total running time of our algorithm. And we simplify that a little bit, and we'll talk about that. In this case, once again, this is some operations and the time it takes in nanoseconds. You can do billions of these operations and then figure out and then kind of say, okay, a billion operations took X seconds, so how much would each operation take? And that's kind of the idea here. And yes, the thing to always worry about is strings. So some things you have to be more careful about. Arrays is usually a factor of n. Usually these things are just some constants, but things like array allocation is a factor of n as to how much time you're actually, what's the size of your array. So it actually depends on the size of the array. Same as the 2D is order n squared. Length may be a constant, but the concatenation is not, because you may actually traverse this entire two strings throughout. So it's not really a constant. As you can see, length can be constant because you're probably storing the length somewhere at the header or something like that. But the concatenation is not a constant factor. So you're actually paying a big penalty whenever you do string concatenation. So one sum is order n. Okay, so what he's trying to do right now is trying to figure out the given a problem, let's say two-sum problem, where you're just trying to sum how many given any integers, how many sets of 2 sum up to 0. You can do multiple. The right thing to do is you go around each of these statements and give them a cause. In this case, variable declaration. How many times you're declaring a variable, etc., etc. But the simplification factor, what we do is we take the largest of these various things. It means that, okay, the largest is probably this array access, which is order n squared, which is n into n minus 1, and you say that everything else, as n grows grows bigger, n and all of those things, they do not grow as fast as that. So this is what dominates this entire algorithm. It is n squared. So you say, for all practical purposes, you say that's what you analyze with and you go with. You simplify the problem, that it's an order n square problem. And I am using the word order before I actually go to it, but you get the idea. So we spoke about that okay, this is the dominant factor, and that's what you come up with. Okay, you say order n square. And so there are different notations. One is the tilde notation, which is an approximate notation, and that's what we do. We say that, hey, that's what we are most worried about, order n square accesses. So we basically came to that. Okay, so this is important. It is the cost model only tilde notation. Some sums, which is fine. I think this is important. What is log n? Log n is integral of 1 by x raised to 1 to n. So I think this term is just important. I think you should keep this into mind, that whenever you see 1 plus 1 by 2 plus etc., that's what log n is. So we talk about these things, mathematical model. I think this is also pretty neat. It shows given how do various functions grow. as you can see, constant is kind of flat with t. It's given whatever n, it is constant. Logarithmic is slightly more than the constant. This is n, this is n log n, this is n square, this is n cube, and this is exponential. Exponential, as you can see, really takes off. Okay, this is exponential, 2 raised to n, correct? It really takes off. So remember this graph, right? So as you can see, you want to ideally be in this linear arithmetic at most, right? N log n. The moment we go to quadratic and beyond, it's just very hard. And there is a very nice chart that explains this. He talks about all of these things. Okay, but this is kind of the most, I think, is a very important chart. It talks about that. Okay, given the growth rate of algorithms, what is the size of input that you can now handle? Even you can see that with n and n log n, you can still do hundreds of millions. With n square, it drops to tens of thousands. So from hundreds of millions, you go to tens of thousands. And and beyond that, as you can see, it really didn't matter much, right? Thousand and thousand. So it's kind of, with 20s, you can now do maybe 30 after 10 years. So even with the supercomputer or whatever, that's what you can do. But that's why you can imagine why NP complete problems are hard and why you need some approximate solutions. So binary search is, so we know it's a login in search. And okay, so there's one important point here. Turns out a lot of people still write buggy binary search implementation, and the most important thing is this sentence here. If you just do LO plus HI divided by 2, you may get into a integer overflow situation. Hence you want to do this. Okay, so this I think is very interesting. And this is the mathematical analysis as to why when you divide this problem into halves plus 1, why this is an order n, or why this thing takes log n times to solve. Okay, so it is, as you can see, it is 1 plus 1 and t of n, and it is this t of n by n. So this whole thing is 1 plus log n. That's what it boils down to. Okay. Now, because you know why, right? Because you are actually every time you do half, you are going to you are halving this quantity, so you only have log n of these things. Once again, why it's log n of these things? Because 2 raised to log of n is n. That's the basic idea, right? So how many times you can divide a value n by half? It's log n, log to the base 2 times. That's the basic idea. Okay, so now let's look at n square log n algorithm for 3-sum, and the idea here is you sort. Okay, so you take minus 40 and 20, and then to search for plus 60, you can then search for plus 60 in this particular range and see whether you can get plus 60 or not, and that is log n times. So hence, even if you sort using n log n, this n square is still quadratic. So, and then you do n square times log n. So it is suddenly you went from n cube to n square log n. Okay, so that is you as you can imagine, you definitely did much better than n cube. Okay, and some more things, theory. Okay. So now what kind of analysis you do? Do you best case, worst case, or average case? What does best case do? Best case mean, given binary search, you might be able to get the element in the first pointer itself. Now that's a best case. Worst case, you might search the entire thing and may still not get it. And the average case is somewhere in between. Half, between somewhere in the best case and the worst case. Now think of the brute force. All of them is n cube because you have to do n cube stuff. But binary search, best is 1, you immediately find. Worst is log n. What that means is you go throughout searching all those various halves and you still can't find. So you kind of empty and you can do at most of log n searches. And the average, as you can see, is still log n. Right? So the way I think about it is sometimes maybe not very good, but 1 plus log n divided by 2. But that's not the right idea. But I hope you can see that on an average you will do log n searches. And so the idea is this is the lower bound on cost and this is the upper bound on cost. And average cases, typically that's what you expect, right? These are rare extremes of the cost, and average is somewhere in between. the interesting thing is when the best case is equal to worst case, you know that okay, that's your algorithm. That's the best possible algorithm. Whatever algorithm you have is the best possible one. So you may do different things. You may design for the worst case, or you may design for the average case. It really depends on what kind of scenario you're trying to solve. What's the problem you're trying to solve? Okay. So we spoke about this a little bit. Okay, let's talk about these three notations. There's big theta, big O, and big omega. Big omega is lower bound. What that means is that, okay, you cannot do worse than this. That is big omega. Big O is upper bounds. That means that, okay, you cannot, sorry, no, okay, sorry. Okay, big, I told something incorrect. Big omega is develop lower bounds for the algorithm. It means that you have to at least take this much time. Big O is upper bound. It means that you cannot, this is your worst case scenario. And big theta is the actual analysis, okay? And that's what we typically use to classify algorithms. But people are in general very kind of, I would say, lenient, and we just say big O notation. We are not theoreticians, so we can kind of let that slip by and still be okay with it. And in this case, Professor mentioned that he is going to talk about tilde or tilde notation, which is the approximate thing. Okay, so in this case, for example, with one sum, the upper bound is that, okay, you have to go over each of them. So the big O is order n. Okay, so that is upper bound. You have to, so this is big O is for upper bound. What it means is that of the optimal algorithm is this. What it means is, and the lower bound is no, upper bound is a specific algorithm, lower bound is no algorithm can do better. You have to at least read all of them. So that's the lower bound, right? You cannot do better than order n. You cannot do better than, and upper bound is, what is the upper bound? What is, for this particular thing, what is the algorithm? In this case, you will see that the lower bound is equal to upper bound. So the algorithm that you have is the best possible algorithm. It's optimal algorithm, right? Okay, so there's one thing I want to clarify. Upper bound is for a specific algorithm, correct? And in this case, three sum, we know the upper bound, but we do not know what is a lower bound for this, and that is why the problems are hard, right? Because when you know a lower bound, you say, okay, well, my algorithm is the same as lower bound, so it's a most optimal algorithm. But when you don't know, that's when you get into trouble. Okay, so we did say that, but we know there is a lower bound, right? A lower bound is order n. You cannot do, you have to at least read all of them. But then, do you now have a optimal problem? We improved this by sorting, but do we know n square log n is the optimal one? We don't really know that, but we kind of know. People have proven that you cannot do better than subquadratic, like you cannot do better than n square. Okay, so what's the approach? You develop an algorithm. You prove a lower bound for that algorithm. You lower the upper bound. You can discover a new algorithm, or you can raise the lower bound. And that's kind of what you do, right? So you start with something that, okay, you have to at least do this much. Then you come up with the algorithm, say, okay, this is what I'm doing now. Can I go down, right? And you try to meet this lower bound. In this case, for the triple sum problem, the lower bound was n. So you can see, can you ever do n? That's the idea. So we said that, typically tilde is what we are going to use. And this is the common mistake people do, interpreting big O as an approximate model. Okay, so people say that, but that's not really right. But that's what we typically end up doing. That's it, theory, memory. Okay, so the last thing is we talk about memory constraint. I'm just going to skip this in the interest of time. But the basic idea is we talk about how much memory is our algorithm going to take. That is an very interesting analysis. We should do that. I'm just going to rush through this in the interest of time. And it talks about machine. I just assume these things are known to everybody. For 32-bit machine, it's 2 raised to 4. For 64, it's 2 raised to 8, 64-bit, and things like that. It talks about how many bytes, a reference, how many bytes does it take to hold a reference to these things, and then about arrays, you have to now also hold the content, so hence it's 4 times n, where n is the sign of the array. For double, it's basically how many number of bytes it's needed to hold the double. As you can see, if long and double both are 8, then obviously double is less precision than long, and things like that. Okay, so think about it. If it is date, then you have to add all of these things. There is some object overhead because this is for the reference, right? If something needs to point to this date object, and there is some padding because you want to kind of, if it is a, depending on whether you have a 32-bit or a 64-bit machine and things like that. Okay, so that's it. Okay, so we kind of end lecture, the lecture series 3 with these things. And now going forward, we'll look at specific algorithms. Thanks. Bye.